Hello everyone, it's July 22nd. The morning session, love it. I feel fresh. I got enough sleep last night. Let's take a look what we have. Partition array into disjoint intervals. Oh, disjoint intervals? Union and find? Given, or I don't know how. We have snippet for union and find, but again, if you ask me to write union and find right now without any references, no, I cannot. Given an array partitioned into two contiguous subarrays, left and right, so that every element in left is less than or equal to every element in right. Oh, that's like binary tree. It is binary tree. Left and right are non-empty. Left has the smallest possible size. Return the length after such partition. Hold on. No, it's not, because it's partition. Alright, it's not taking everything out. We can regroup, so it's not binary tree. And it's not union find. Although, I think I have to look at union find every day and look at the BIT, the binary index tree every day, just so that I will be able to do it without reference. Anyway, let's focus on this one. We have 30,000, okay? At least one way to partition norms exists. So we want two subarrays, yes. Not subsequence, subarrays. Left and right. Okay? Everything on the left is less than, so no, not 5, not 0, 3. Okay, that's 3. That will be 1. We'll have to find the smallest. Oh, okay. So we need to find the smallest. Oh, no, it's not just smallest. I feel like I have done something similar. I mean, definitely we need to find the smallest. That's for sure. But as we finding the smallest, we also need to keep track of anything that's kind of big, and then we kind of look to the next one and see if this one is smaller than the previous one. We have to keep going until we reach a value. Right, so we have to first cover the smallest, that's for sure. Right, so we need to find the smallest. That would take O(n) to find the smallest. And well, can we find it along the way? Yeah, that's fine. We can find it along the way. Along the way, we keep track of the smallest. If the smallest has not been found, we have to keep going. There's no other way. Once we found the smallest, then the task is we need to track the biggest that's been found so far, such that the remaining has to be bigger than the biggest. Right? That's the thing. So we find the smallest. That's good. And then we also keep track of the largest. We have the index of the largest. Now we don't really need the index of the largest. We need just the value of the largest. So now after we find the smallest, we keep going, and we just compare to the largest. If it's small, we keep going. If it's bigger, the first time it's bigger. Yeah, the first time that a value is bigger than the biggest value encountered so far, we need to record this position. That's a potential position. And we just keep going. If the next one is bigger, then we don't change it. If it's smaller, then we have to update. Right? We have to update. Update to like -1. So like now we have to find a new one. Yeah, because I have to. Yeah. I think that shall do it. It will be O(n). So just a couple of things to keep track, and not just have to keep track the largest so far. We need to keep track the minimum so far, and we need to also track the index of the first value that's bigger than the biggest value we have encountered so far. Wow, this is a very long sentence I just said. All right, so we have the max so far, right? Min overall. Oh, we also need min overall. We don't know min overall until we figure out the entire thing. All right, that's just, we can call it define. Or let me think. Can we do one trip on the min overall? Yeah, because max so far, min overall. It's too long. MA and MI. Max, min. What else do we want? Like max or min, and we want the index, right? Index. Oh, so max min, we just use first value. That's fine. Doesn't matter. 0, 0, and the -1, right? And for n, for in enumerate nums. I go through the nums, and we say, all right, this is the key. We say if if n is smaller than minimum, right? If it's smaller than minimum, then index equals -1. We need to reset index. We find a new minimum. If n is larger than minimum, we don't care. How about the max? So if it's smaller than max, right? Smaller than max, then we need to also reset index, right? If it's smaller than max, then we need to reset index. If n is larger, equal to, right, max. If it's larger equal to max, index equals I. Oh, and then we check if index is smaller than 0, then we set index to I. Otherwise, we don't care. All right. So we consider n in relation to max and the min. Then what? Actually, this one, mi equals n. I need to do this. If n is larger than max. But how do we update the max so far? Well, if it's larger, hold on. If a value is smaller, then we reset index. If a value is larger than, then we record the index here and then we move on, right? We'll move on. And how do we know which one is the max? Then we start from some value, right? We start from some value, and if we got something bigger, we don't care. If we got something smaller, then the max needs to change. The max needs to change once we hold on. This one, the minimum, but do we really care about the minimum? We don't care about the minimum, right? We don't care. What we care about, why do we do the minimum? What we care about is the current max. Yeah, that's the thing we care about, the current max. If it's smaller, then if we have something smaller, right? That's fine. If I have something bigger, then potentially we need to change it to this one. So we need to record it, the potential big, right? And then the next one is big, potential big, and the next one is small. Then and what? Hold on. I might be able to do it an easier way. We push. I'm thinking about monotonic stack. I push it in, it's smaller, it's smaller. I push it in, it's bigger. Okay, and push in. How would that idea work? So we keep pushing, and if it's something smaller, we just keep pushing. If it's something bigger, then we pop, right? So, we pop. Everything on the right side needs to be bigger than on the left side. If it's smaller than the current max, right? We're talking about the current max, then I keep moving. Smaller than current max, then I keep moving. If it's bigger than the current max, then it could be the solution, but it depends on whether we have something small. Something smaller than what? And the previous max? No, it could be something small. This one is smaller than this, but this one's bigger than this, right? So we just keep check on this one, right? And then if there's something bigger, we move on to this one. If it's something bigger, we'll move on to this one. If it's something smaller, if it's bigger than this, but smaller than this, then we don't move until we hit something. Okay, so let's do it another way. So what I say is current max, and we have a potential max, right? Current max, potential max, and then we don't need to consider min. We just say if it's smaller than current max, we reset the index. We don't care about the index. Move on. If it's larger than current max, right? If it's larger than current max, then we need to compare. If it's larger than current max, then we say, okay, right? Say else it's larger or equal to current max. Then we check the index. If index is smaller than 0, that's the first time it's larger. We set index. And then we need to go the potential max. So we say if n is larger than potential max, then potential max equals n. Otherwise, we don't change the potential max. So keep going. If it's smaller, boom, we reset. And actually, when we reset, right, current max shall equal to, if we reset, current max shall be the potential max. Right, current max, we're going to update the potential max. If it's smaller, right, then we're resetting. If it's bigger than n, right, so n is bigger than, but it's smaller than potential max, we don't change the potential max, and we don't do this. And eventually we're going to return index plus 1. I think that's the length. All right, let's try this. Yeah, I've not been able to do monotonic array for a while. I mean, we can do increasing, right? We can do increasing or decreasing. Yeah, that can be done in OM. Anyway, so this is the first test case. 5, 0, 3, 8, 6, 3. Next one is 1, 1, 1, 0, 6, 12, and 4. So references. Nums partition disjoint nums. Check it out. Oops. Ha. Oh, index. Yeah, because index is pointing to the first possible bigger one, the bigger one. So it has to be just the index. Then we pass both. All right. Test case. What do we do? Some interesting test case. Okay, some interesting test case. Wait. 0. I just call 0. That should be 1. My answer is 0, which is not correct. Okay, that is not correct. So we need to make changes to our algorithm. So it should be 1. Then like first additional test case and we fail. All right. Oh no. Okay, so current max, potential max equals 0, index is -1. And we go first one, smaller no, larger than equal to index, so index equals I, right? So index equals I. Yeah, we set hold on, larger or equal to. We might be able to such that every element on the left is less than or equal to every element on the right. Therefore, if the value is smaller, then definitely. If my current value is bigger or equal to what we have before, then I set it here. I think that is the problem. If this value is larger or equal to, what does our index represent? Our index, what I want is our index represent the first value on the right partition, right? If it represents the first value on the right partition, then that means we might be able to solve this just by, because we're checking on this, right? And the index on the right partition is -1. It might be able to, how about we don't do it this way. We say in range 1 to land nums, because we just avoid the first comparison. And we'll just say n equals nums I. Then we pass, right? Then we pass. I think the problem is that we're going for the leftmost, and when we hit, if the smallest is the beginning, then this is the index is stuck here, right? Then these two will pass as well. No, tuple object is not callable. That's because I forgot to put a comma. Okay, so this one passed that. And we can actually save it one line. Let's save this line. I think I can just do this and do this. Right? What else can we save? We can call it elif. Elif index is smaller than 0. Then we do no, actually that's not right. These two has to be done together. Undefined name n nums I. Alright, I'm gonna try something else. What else am I thinking about? How about a decreasing? So let's say 6 if decreasing. A decreasing. Oh, a decreasing. That will give us error because there's no partition. Yep, invalid test case. So we have to have a partition, which let's just give it 9. Now we have partition. So this shall return 5. Just give us 5. Okay, that's good. How about everything's the same? 1, 1, 1, 1. That should give us 1. All right, I think we're ready. All right, take a look. Pending, judging, accepted. Nice, we got it. So the idea is to check to iterate, right? Iterate through nums and check the current n with against the max value so far. If n is smaller than current max, then the left partition must start after n. If n is larger or equal to current max, then the left partition might end right before n, but yet we don't know that for sure yet. Furthermore, we must track the next potential max. This is because if we encounter n larger or equal to current max, and after that we encounter something. If we encounter n1 larger, but we encounter n2 smaller than current max. If this and after that we encounter, then we must update current max with n1. In the algo, we call such n1 as pot max, potential max. We iterate through the entire array. Keep track. Did you see keep track? We might right before n. We keep track of the index of such n as a potential solution to the problem. As a potential to the problem. Furthermore, we must track the next potential max. That's correct. After that, blah blah blah. We must update with entire array, and the solution is the final recorded index. Index. ON, I don't think this explains very well, but you read the algorithm, it shall make it very clear. So it's ON, should be middle in the pack. Oh, actually it's not middle of the pack, it's front of the pack. 176 milliseconds, 92% ranking. All right, let's go to problems. This is a medium. Yep, pretty sure it's a medium question. Yep, medium question. 915. I do not think I've done this before. Solution is available. Nope, it's my first time. All right. What solution do we have? Next array, approach 1. Oh, that's it. Oh, very short. Instead of checking whether all for L in left, for R in right, let's check whether max left is smaller than min right. All right, what is this? For L in left, for R in right, all L smaller equal to R. We check the max left is smaller equal to min right. That's true. If I find the max subarray, max left, specifically max will be the maximum of subarray related to each other. Yeah. Min right. So we keep track max left and min right. Okay, so what do we say? I mean, this is to create both. And then if max left is smaller than min right, then we return I. Okay? How do we do it without on space? I mean, we can iterate through. And we iterate through from the other side. Alright, max left is smaller than min right. I don't know. Let's see. To avoid max left, max encountered, max and max. These are like a long solution, but I can only see like part of it. I don't know why. Anyway, let's go to discussion. We must discuss this. All right, into two subarray, I got that. Left max and the right min. I can do it in one pass. Oh. The left part, middle part, and the right part to be processed. Keep global max as the maximum number from 0 to I minus 1. We're iterating I from this. If num I is smaller than left max, nums I can't belong to the right subarray. Max left equal to max. So num I belong to the left. The repartition, update left max equals global max. Is this like something similar to my idea? Partition, that's like my index. So, but this one keeps track on the global max. All right. So we say if the current value is smaller than left max, partition equals this one moves partition to here, which is fine, and left max equals global max is this one. But there's no else. There's no else. Let me see. Global max. If a value is smaller than the left max is what we have seen so far, right? And if the current value is smaller, then we put the partition at that, right? And then we keep going, and then left max will have to equal to global max. That's the potential max. That's the potential max. So left max has to equal to potential max, and then we keep going. If it's smaller, then we keep doing. If it's bigger, then we don't consider, but we update. We always updating, which means this thing is always doing. If it's smaller, yeah, this is to compute the maximum. It's the same idea, but I like this one better. Looks nicer. Yep, I think this is good. I'm just gonna use this. It's the same idea, but better implemented because they don't have to do this, right? I set a partition at the first position of the right array. They set a partition as the last element of the left array, and because of doing that, we don't have to go through this part. Good, very good, but the result will be the same. Yeah, so solution 2, solution 1. So this is from, oh, I forgot to copy a link. From this. Same idea as solution 1, but since the partition is tracked as the last element of the left partition, left array, the algo is simplified. So, and now we're going to be current max and global max, and a part partition. And when it starts at 0 and 0, so this is exactly the same. But partition is going to be 0 now. Partition is going to be 0 now. So what we're going to do is 0 plus 1. Then for I in range, I want to land nums, right? We are always going to say globe max equals max, globe max, and nums I, right? That's the global max. We keep track. And we say if n is smaller than current max, right? If it's smaller than current max, then we cannot use it, right? Then we update. Partition equals I, and current max equal to global max. Because we do this, anything we have seen so far that's bigger than the current max, we need to update it. Lord, that's it. Part plus 1. Man, nums I. Nums I. Yep. Alright, submit this one. Yeah, it is much easier to write, and the logic is actually clearer. And we just need to swap it a little bit. Alright, that's it. That's it for today. Good work. I'll see you guys tomorrow. Adios.